Ladies and gentlemen, today's class recording has started. So, over the past 3 days, sorry, I wasn't prepared. Pull this up here. Over the past 3 days, we have been working on this picture, right? And just to review, we said this is a picture that shows us what? Orbitals, right? And our definition of orbital is what? Probable locations of electrons, right? That we don't know exact locations, but these are probable locations. And over the past couple days, we went through and we used our quantum numbers to distinguish these orbitals from all the other orbitals that were in the picture. At the end of class yesterday, we talked about the idea that each orbital can only hold a maximum of 2 electrons. And so we went through and we assigned 4 quantum numbers to each orbital, or we can assign 4 quantum numbers to each orbital. We didn't do it with every single one, but we talked about these 4, right? N. What quantum number is represented by N? What do we call that quantum number? The principal quantum number. Good. All right. So what does the principal quantum number tell us about an orbital in general? Its energy level. And that relates to what in terms of its location? How close or how far away it is from the nucleus. Okay? So the principal quantum number relates to its energy, how close or far away from it is to the nucleus. All right. Letter L. Does anybody remember what letter L is called? The angular momentum quantum number. Essentially, what does the angular momentum quantum number describe for us, Ella? The shape of the orbital, right? And so we talked about 4 different shapes that we have, right? So somebody want to give me a description of one of the 4 different types of shapes? Sam, what's one kind of shape that we talked about?
Isn't it like an S?
An S orbital. What does an S orbital look like?
It's a sphere.
It's a sphere, all right? So that's one type of shape that we talked about. What else we got? Anybody else want to take another one? Lorenzo, go ahead. The hourglass orbital is a p orbital. Good, all right? Say what else? The butterfly orbital is a d orbital. And then the last one, which I haven't really shown you a picture of because this is way too much, f orbital, right? So we have 4 types of orbitals, s, p, d, and f. And the angular momentum quantum number, lowercase l, describes that shape. All right, m. M is the magnetic quantum number. What does the magnetic quantum number describe for us? This one's a little bit trickier. Sam, you want to go ahead? Go ahead.
Indicates the orbital the electrons are in.
It indicates which orbital the electrons are in, because what do we run into sometimes, especially in the p orbitals and the d orbitals? What's true about the quantum numbers of this one, and this one? Or when we found through, what did we find about the quantum numbers? So, first 2 are the same, because they're in the same energy level and they're the same shape. So if the first 2 are the same, we have to have a way to tell them apart from one another, and that's where the magnetic quantum number comes in. Okay? And then the last one we introduced yesterday was the spin quantum number. What's important about the spin quantum number? Sam, go ahead. That's for the magnetic quantum number, okay? The spin quantum number, the last one, the letter S in this picture. What's important about the spin quantum number? Someone besides Sam want to help? I'm just going to answer a couple questions already. But, what's important about the spin quantum number? Sam, go ahead.
It shows like each orbital can only hold 2 electrons.
It shows that there's a maximum number of electrons that each orbital can hold, right? And Sam, what is that maximum number that each orbital can hold? How many electrons can each orbital hold?
2.
Just 2, right? So each one of these shapes that we've drawn over the past 4 days or whatever it's been, right? Each one of these shapes can only hold 2 electrons, all right? Good there? Okay. So today, we start talking about orbital filling. What we'll find is that even though all of these locations exist, we don't always find electrons in all of them for a couple of different reasons. And we'll talk about those reasons starting today. You'll find that the presentation today is pretty boring. It's just black writing on a white background, because we're not going to spend a whole lot of time writing stuff down in outline form. We're going to spend a lot of time doing stuff, all right? So there's going to be a lot of times we're not going to be writing up on the board. So the fact in the background isn't real exciting. Don't worry about it because we're not going to spend a whole lot of time doing it. Okay. Let's go here, let's go here, and let's go here. Okay. So today, determining which orbitals have electrons in them, the main idea behind that is something that we call the off-bow principle. Okay? So the off-bow principle says that orbitals are filled from lowest energy to highest energy. And this theme with energy is something that we will keep coming back to. That if objects are left to their own devices, or naturally, they will migrate to lower energy locations. Okay? If we drop something in this room, where does it end up? On the floor. Okay? I'm going to ask you a question, and you're going to all answer it incorrectly the first time. But then I'm going to ask you this question like 50 times this year. Hopefully by the end of the year, you'll get it right. Okay? Why does the ball end up on the floor when it gets dropped? No.
No, the attraction to the center of the floor.
Gravity is how it ends up on the floor. Mo, why does it end up on the floor? The energy of the ball is lower on the floor than it is up here. That's why it ends up on the floor. Gravity is how it ends up on the floor. Okay? Things left to their own devices will gravitate towards a lower energy state. Electrons go into lower energy orbitals before they go into higher energy orbitals. Meaning, which orbitals are going to fill up first? Where do we find low energy orbitals? Close to the nucleus, right? Electrons closer to the nucleus have less energy because they are in lower energy orbitals. Orbitals closest to the nucleus contains lower energy, and that means that they get filled up first. And as a pattern, right? You guys have a big chart that shows up right in the middle of the first page. And then it's actually two separate charts, but they tell us the same thing. Okay? So, for starters, if we read along the outside edge of either one of these charts, let's start with the one on the left. I like the one on the left better than the one on the right, but they both tell the same thing. What does it say on the outside edge of this chart on the left-hand side here? Increasing energy of electrons in orbitals. Meaning, which way are we going to read this chart? We're going to start where? Well, where on the y-axis are we going to start? Down at the bottom, right? Because if the arrow points upward and it says increasing energy, that means we want to start at the lowest energy. All right? So we're going to read this chart from bottom to top. Okay? Same thing with the chart on the right-hand side. It says relative energy. We introduced that term relative a little bit earlier in this unit. When we describe something as relative, what does that mean? We say like the relative mass or the relative energy. What does that mean? Say again? Probable, maybe. Is it actually a value? No, it's more of a comparison, right? So here, if this is relative energy on the right-hand side over here, the chart on the right-hand side, that means that ones towards the bottom are going to be lower energy than the ones towards the top. Okay? So we're going to use this chart a bunch today. We're always going to read it from the bottom to the top. Okay? We're going to use this chart to make something that we call an orbital diagram. An orbital diagram shows us how the electrons are distributed within the actual orbitals. The picture that we drew starting last week on Thursday and that we were working on over the past couple of days, that is a picture of orbitals. But, like I mentioned earlier, that doesn't necessarily mean that there are always electrons in all of those orbitals for a couple different reasons. So an orbital diagram shows us, okay, where are these actual electrons, or where are these electrons actually? There's a bunch of places where they could go, but where do they actually end up? Okay? So, an orbital diagram. We use circles or lines or boxes to represent the different orbitals. Different textbooks will present them different ways. I'll kind of use a variation of these different things just to kind of give you guys an idea that it really is the same thing. It's just a different representation of the same thing. So depending on which book you read, sometimes they'll use circles, sometimes they'll use lines, sometimes they'll use boxes. But they almost always use arrows to represent a single electron. And so you'll see some combination that looks like this, where the circle, in this case on the left-hand side here, is representing an orbital. The one on the left is an orbital that only has one electron in it. The one on the right, this circle here, is an orbital that represents two electrons. Will we ever see more than two arrows in a circle? No. No, because each orbital can only hold how many electrons? Two maximum, right? Over on the right-hand side, same information, just represented differently. So here we have lines to represent our orbitals, horizontal lines, and then we draw the arrows above them. Okay? Good? All right. Now it comes down to the actual doing stuff part. So, at the bottom of your outline, you'll see that Roman numeral number 3 says orbital diagram practice. And the first orbital diagram practice that we're going to do is drawing the orbital diagram for hydrogen, all right? And we almost always start with hydrogen, right, for two reasons, okay? First, why would we start with hydrogen? One electron, right? And two, hydrogen is the most common atom that we find in the universe. If we look at all the atoms in the entire universe, hydrogen is the most common by a long shot, okay? So it makes sense to start there. All right, if we are going to draw a picture that represents where electrons actually are in an atom, the first thing we need to know is how many electrons do we have to worry about, all right? So in this case, we only have to worry about how many? One. And how do we know that we only have to worry about one electron for hydrogen? That's hydrogen's what? Atomic number, right? We said the atomic number tells us about two things of the atom, right? What does the atomic number describe for us for an atom? What two things does the atomic number tell us about an atom? Number of protons and the number of electrons. So, you guys have already done this, so you know this in your head, right? But when we're talking about hydrogen, we only have to worry about one electron, okay? So, here we're going to start off, and we're going to draw something to represent our first orbital. I'm going to start off, and I'm going to draw a circle to represent my first orbital, okay? Just a blank circle right now. But, like we talked about on the drawing that we drew on last week, or at the beginning of this week, there are tons and tons and tons of orbitals. But not all of them have electrons. This chart that's at the front on the front page tells us which orbitals do we actually fill up. And we said we're going to read this chart from where to where? Bottom to the top. So we start at the bottom. And what's the first orbital that we run into on this chart? 1s, right? And so, this blank circle, this blank circle that I drew here, I'm going to label it as the 1s orbital. The fact that this orbital is labeled as 1s should tell you two things about it. The fact that we've labeled that circle to represent the 1s orbital, it should tell you two things about that orbital. What should it tell you? Brooke, do you want to get into it? Not that it has one electron. Okay? If it's the 1s orbital, it should tell you two things. Brooke, can you go ahead and do it? Okay. What else? What is the fact that I called this orbital 1s? There's two things you should be able to tell me about it. Lorenzo, what's one thing? It's an s orbital, and that means that we should know what about it? It's spherical, right? So that's the s part. What does the 1 part describe about it? It's the first one, meaning what? It's in the first energy level, and it's close to the nucleus, all right? So if we label an orbital 1s, you should be able to tell me, okay, it's close to the nucleus, it has low energy, and it's a spherical orbital, okay? All right, now, as far as the electrons themselves, like we said here, how many electrons do we have to put into this orbital diagram for hydrogen? Just one, all right? So, and we said on the previous slide, right, what do we use to represent our electrons? Arrows. And so I need to put one arrow into this circle, boom, just like that. Sometimes like here when I'm drawing them, I'll use just one-sided arrows instead of two-sided arrows. You can use two-sided arrows if you want to. I don't really care, as long as we use it to represent. There's the orbital diagram for hydrogen. It tells us how many electrons are there and which orbitals those electrons are actually in. Good? Okay. Flip it over to the next page, right? What shows up at which one's next? Helium. All right. So if we're going to draw an orbital diagram for helium, right? An orbital diagram tells us where electrons actually are. And so before we draw a picture that shows us where electrons actually are, we have to make sure we know how many electrons we have to place. How many electrons does helium have? 2. And we know that because that's helium's atomic number. Okay? All right. So this time, instead of drawing a circle, I'm going to draw a box to represent my orbital. It really doesn't matter. Like I said, circles work, boxes work, lines work. It's all kind of the same thing, it's just a different representation. First, we have to label this orbital, right? Meaning we start on this chart from bottom to top. What's the first orbital that we run into? 1s. So I'm going to label this as a 1s orbital. Okay? Good there? Okay? Now we start placing electrons. Here's electron number 1. Is this orbital full? No. How many electrons can this orbital hold? 2 maximum, right? But just because there's 2 electrons in there doesn't mean we don't have to tell them apart, right? When we have an orbital that has more than 1 electron, 2 electrons, we have to distinguish each of those orbitals. And the way we do that is by flipping which way the arrow points. So this one represents the first electron, and then that one represents the second electron. So now we can tell them apart from each other. Okay? Say again? So like I said, it doesn't, like some books, it kind of just depends on, like different textbooks use circles, different textbooks use boxes. It really doesn't matter what we're using to represent the orbitals. I just want to show you that it's all kind of the same thing. So if you want to make them consistent, if you want to use circles the whole time, that's fine. If you want to use boxes, you can do that too. I'm going to draw them kind of some different ways, just so to make sure that you guys understand that it really is representing the same thing, just in a little bit of a different way. Okay? Sam, go ahead. This is a representation of an orbital. Okay? So this is not a picture that, this is not a picture that represents or that shows how the orbital is shaped or how the orbital is, how big it is or something like that. This is a picture that's going to represent where those orbitals, where electrons actually go within those orbitals. So you'll see in a second, when we do the next one, we're going to have to go up from 1 orbital to 2 orbitals. They look exactly the same when I draw them. We just label them differently. Okay? All right, good? So this is our first example of another rule that we use when we're drawing orbital diagrams to show us where these electrons go, and that rule is called the Pauli exclusion principle. We introduced the Pauli exclusion principle yesterday. The Pauli exclusion principle says each orbital can only contain 2 electrons maximum. And when we have an orbital that has 2 electrons in it, we distinguish those orbitals from each other by drawing 1 arrow up and 1 arrow down. Okay? We say that they have opposite spin, but notice that opposite spin is in quotation marks. They're not actually spinning in different ways. That's just how we distinguish one from the other. Okay? Good? Yes, Mo? That's what's going there. Yeah, opposite spin. So, okay. But notice again, like I said, opposite spin is in quotation marks, right? It doesn't actually mean they're spinning different directions. It's just a way to tell one from the other. Okay? Good? All right. Next one on your list is lithium. Oh, what? All right. First thing we have to do when we are drawing orbital diagrams is make sure that we know how many electrons do we have to place. How many electrons do we have to place for lithium? 3 electrons, because that's lithium's atomic number. All right, so we start off and we draw an orbital. This time I'm just going to use a line to represent my orbital. Okay? We go to our chart. We find the first orbital that we always run into is the 1s orbital. It's the lowest energy orbital. Okay? How many electrons can this orbital hold? 2. Okay? So here's my first electron, here's my second electron. Okay? Is that orbital full? Yes, that orbital is full. But how many electrons does lithium have? 3, but we've only drawn 2 electrons. So we go back to our chart, right? And we move which way on our chart? Up, right? So the first orbital we ran into was 1s. The next one that shows up is 2s. And so I'm going to draw another line to represent another orbital. And I'm going to label that orbital as 2s. Okay? Yes, sir? Oh, we're getting there. Don't worry. Don't you worry. We'll get there. All right. So, Sam, going back to your question from before, right? Okay. Even though those are 2 different orbitals, I'm going to draw them the same way because I'm just representing an orbital, and I called it 1s and 2s. Okay. The fact that it's a 2s orbital, that I've labeled that line as 2s orbital, that should tell you 2 things about it. What should it tell you about that orbital? The fact that I wrote 2s underneath it. It's spherical. That's the s part, and it's a little farther out. It's the second energy level. So it's a little farther out, and then Anka, that means what about the electrons in it? They have a little more energy than the ones that are in 1s. Okay? How many electrons do we have left to place? Just 1. And so I'm going to draw it like that. Okay? There's my orbital diagram for lithium. Okay? Good? All right. I'm pretty sure the next one that you guys come across is boron, yes? All right. All right, for boron, first thing we got to do, how many electrons do we have to place for our boron orbital diagram? 5 electrons, because that's boron's atomic number. Is that okay? Oh, there's notes in between?
For boron.
Oh.
Kilo.
Let's do this first, and then we'll fill in those notes. Okay? Yeah, yeah. Grace, we'll do these first, and then we'll fill in those notes. Okay. So, first orbital, right? We always label that first orbital as what? 1s. It's the lowest energy orbital that shows up on our chart. It's always the first orbital to get filled. How many electrons can this orbital hold? 2. Here's 1. Here's 2. left, 2 down. How many to go? 3 more to go. We move up this chart. Next orbital that we come across is what? 2s. So I'm going to draw another line. I'm going to label that as 2s. How many electrons can that orbital hold? 2. And so I'm going to draw an arrow here and an arrow here. All right, how many down? 4 down. How many to go? 1 to go. So, can we fit any more electrons in these orbitals that we have drawn? No. Nope, these are all both full. So, we said we read this chart from bottom to top. Okay? As we go across, right? As we go up from the bottom, what's the next lowest orbitals that we run into? 2p. Now, if we look, though, on this chart, or if we remember from our picture before, how many 2p orbitals are there? 3, right? One of the 2p orbitals goes along the x-axis, one goes along the y-axis, and one goes along the z-axis. Good? Okay? So, much more important to our orbital diagram, though, if we look at these 3 lines representing the 2p orbitals, what are you seeing about how high they are from the bottom of the chart? How high are they in relation to each other? They are the same height from the bottom of this chart. Like these 3 lines right here? Yeah? If you look at how far they are from the bottom to the top, they're the same height. Grace, what does that mean about the energy of these 3 orbitals? They all 3 have exactly the same energy. When we come across a situation like this, there is no advantage to electrons going here, here, or here. They're all exactly the same. What does that mean? It means when we're drawing an orbital diagram, we have to draw all 3 of them. They come as a group. They are like a trio. Okay? We're going to run into some quintets a little bit later on. So. Yeah. Yep. All right. We've drawn all 3 of these orbitals, but how many electrons do we have left to place? Just 1. Now, going back to that discussion from before, if all 3 of these are exactly the same energy, is there any advantage to that 1 electron going into one on the left or the middle or the right? No. All exactly the same. It really doesn't matter. For the most part, you'll find that when books write out orbital diagrams, they would put the 1 electron there. Okay? However, if you did this, you're just as right. Okay? Or if you did this, ready? You're just as right. Okay? There is no advantage to one of these orbital diagrams versus one of these orbitals versus the other orbitals. Okay? Any one of those 3 that I just drew is just as right as any of the other 2. Okay? Because each of these orbitals has the same energy. Okay? All right, to fill in your outline, okay? When we run into boron is the first time we run into p orbitals, so we run into the p sublevel. When sublevels are drawn, we draw all those orbitals, meaning we can't just draw one of the p orbitals, we got to draw all the p orbitals that show up. Okay? All right, good there? Yes. All right. Now, here, there is a right or wrong for the next one. And the next one that we're going to draw is carbon. Okay, so you look on the periodic table, you find carbon's atomic number, and it's 6. Okay? So that means we have to place 6 electrons. First orbital is always going to be what? 1s. It's the lowest energy orbital. How many electrons can that lowest energy orbital hold? 2. So we're going to go here, 1 and 2. Okay? Next lowest energy orbital we run into is what? 2s. It's the next one up from the bottom. How many electrons can that 2s orbital hold? 2. There's 3 and there's 4. All right? We still got 2 more to place. We use our chart. The next lowest energy orbitals that we run into are 2p. But just like we discussed, how many 2p orbitals are there? There are 3 of them. So we draw all of them and we label them all 2p. Okay? Now, here's where the right or wrong comes in. Okay? So, we have 2 electrons left to place. I'm going to put electron number 5 here. Okay? Is that orbital full? No. But when we go to place orbital 6 or electron 6, there's a right place and a wrong place to put it. Okay? So, what did we just talk about in regards to all 3 of those 2p orbitals in terms of their energy? They're the same energy. So it doesn't make a difference whether this electron goes here or here or here. But the next one, it does make a difference. What do we know about all electrons in relation to each other? They're all negative. They all repel. Does the 6th electron want to be close to the 5th electron? No. It really doesn't. And so, will it go into this space right here, even though that orbital is full, or not full? No. It'll go somewhere else, especially because there's no difference in the energy of these 3 orbitals. If you move into a new house with your brothers and sisters, and there's 3 bedrooms that are exactly alike, and your brother takes bedroom number 1, are you going to go into bedroom number 1? No. Probably not, right? Especially if all 3 bedrooms are exactly the same, right? Like, why would you share a bedroom with somebody else if you could have your own bedroom, right? So, orbital or electron number 6 is going to go in a different 2p orbital. Yes, Sarah?
So let's say that, that there are 5 left.
Okay.
Right? So, and so now we have, so let's say now we have 3 left.
Okay.
In, right?
Yep.
So we need to put 1 and then in the last one, right?
Okay.
But then
So
there's 2 left, so you have to put it in the 2, so then they'd be like crazy.
we'll get to that in a second. We'll get to that. Actually, we won't get to it today. We'll get to it tomorrow. Okay.
Okay.
But this idea that these electrons are going to, hold on a second, we're not done with class yet, relax. All right, the idea that these electrons spread out is called Hund's rule. Okay? Hund's rule says that electrons will not pair up in orbitals until each electron has at least 1 electron. They try to distribute themselves as evenly as possible because they don't like each other in terms of repulsion. Okay? All right, so tomorrow we will start talking about when we get past 7. All right? Good job today, everybody. We'll finish this up tomorrow. If you haven't taken that quiz yet from yesterday, please make sure you do. Thank you.